Good morning. How's it going? Get more response, otherwise I'm going to be really sad. Right, so this week we're continuing to discuss Newton's laws, and the next two lectures will be applications of Newton's laws. The lecture today shouldn't be too taxing. It's mostly concepts and mostly about how to start approaching problems. But the next two lectures are going to be quite a lot more intense in terms of doing calculations. So you may find, especially the third lecture, there's just a lot of material. I've tried to put quite a lot into the lecture notes, so you'll be able to read through them and make sense of them after the lecture, or maybe even before the lecture, with a bit of luck. Show you a couple of things while we're getting started. So this is the main Learn page, and hopefully you found out that this section down the left-hand side comes and goes with the little hamburger thingy. These sections are not very friendly on mobile devices sometimes, but so just a reminder that there's, for lecture discussion, you know, if you want to, if you're watching this live streamed and you want to talk to Pratik online during the lecture, there's a Zoom link there, so you actually watch the lecture on Echo 360, but you can talk. You can also have a Zoom session. So it's the Echo link, and it's showing that we're actually live at the moment. So that was the Zoom link. One or two people were confused about uploading their first question from the tutorial if they're doing it online, and there should always be an upload section beside the tutorial for the week. So we're week 3, so this is the information. So this tutorial preparation quiz and the tutorial questions should be available now, and then the post-tutorial quiz and the solutions become available after the tutorial. Timing thing. Now, of course, overview is important. If you have questions, if you have problems with the labs, it's better if you contact Cliff directly, since you're welcome to contact me, but all I can really do is pass it on to Cliff generally. And down here we've got a few things. We've got a course outline, which I talked about probably in the very first lecture, and also an overview of the first term. So this is the week by week or day by day plan. So we're in week 3. So today we're doing forces and Newton's laws of motion. These sections from the book. We're doing a lab this week on finding the g-value from doing a pendulum experiment. And then 8 and 9 are applying Newton's laws. Now on the 21st, on the Monday evening, I think 7, there'll be a test. This will be an online test, mostly multiple choice, so pretty similar to what you've been doing in those online quizzes, but you also need to be able to upload just a single page of PDF. I'll probably get you to draw some sort of diagram just to see how you're going with being able to do that stuff. Just asking you multiple choice questions really isn't quite enough to make sure people are on track. So the test will cover the material for these first 3 weeks first 3 weeks of the course. So we're going to do Newton's laws this week, some more about Newton's laws this week. Then you'll have a tutorial and a post-tutorial quiz. So there'll be a lot of information, a lot of stuff that you'll be doing next week that then we'll test and you'll be finishing next week that we'll be having the test. The lab next week is about forces on an inclined plane, and this is actually quite relevant to the material we're doing this week. Okay. And then the other thing, after you've done all those quizzes, there's a revision exercise for each week which becomes available after the post-tutorial quiz is due, because these revision exercises, every time you run this, it brings in a random selection of 10 questions, which are from the pre-tutorial quiz, the post-tutorial quiz, and some extra stuff. So this is designed so you can use this to review what you did. So let's get on with forces and Newton's laws of motion, part 2. So today we'll be talking about free body diagrams and Newton's third law of motion. And so this is a meme that gives you the instructions. You know, when you want to do some of these problems, you should draw a free body diagram. Otherwise, you'll have difficulty. So, free body diagram. Obviously, I can't spell very well. But anyway, free body diagram basically represents the object you're interested in as a single particle, and it shows the various forces that are acting on the object. So it's a way of starting to think about what's happening. So we have something like this ball on the string. You know, what are the various forces acting on it? And we already started doing this. We say we're going to isolate the object. You know, draw a little circle or something around it. Figure out what the forces are on that object, and that will allow us to translate the problem that's in words into mathematics that we can solve using our physics knowledge. So the sort of thing we do, let's do it while we talk about it. So we have something like this. We have something like this ball on a string. So you've got the ball on the string, and we're just interested in the forces on the ball. So we maybe draw a little box around that. We can also it's useful to draw a coordinate system, either out here or on when we start drawing this, we're going to represent this by a single point, and then maybe that's the y-axis. This is a one-dimensional problem, so we don't really need the x-axis. So the dot at the origin of the coordinate axis. And so what are the forces? Well, there's that tension force pulling it up, and there's the gravity, the weight force pulling it down. And if And if it's not moving, there's no net force. So you might write F net is equal to 0. However, if it was the case where you're pulling on this and it's going upwards, then that tension force is then bigger than the weight force, and in that case the F net is upwards. So hopefully you can see that by doing it like this, you're getting an idea of how we're going to approach this, what are all the forces, and since we're then going to use Newton's laws, it's that net force that's acting on the object that's the key thing, which is going to allow us to figure out what's going on. So here's a little example. Okay, so here's an example of an elevator lifted by a cable is moving upwards and slowing. Unfortunately, I don't have three things, so I can't show you all the. But it's something on a cable and it's moving upwards, but it's getting slower and slower as it moves upwards. So you want to think about what is the net force in that case? Is the net force pointing up or is the net force pointing down? And also what are the actual forces? So what we're doing here. I think you've got 2 people on here. Oh yeah, 6. Much better. So B is winning. And B looks to me like those 2 forces are the same, so I think that would be no net force. I think C has a net force down and A has a net force up. And D is something kind of weird. Force elevator. I mean, but it's very common to end up with some extra, you think there's some extra force there, but maybe there isn't. So this is the answer to this particular question. The elevator is being lifted, it's moving up, and it's slowing down. So that means that the net force has to be in the downward direction. So the gravitational force or the weight force has to be bigger than the tension, so that it's slowing down. Whereas B would be the answer for if it was going up at a constant speed. Another one. So this ball's been tossed straight up. What's the correct free body diagram just after it left the hand? So it's just after it left the hand. So obviously if I throw the ball up, there's a force on the ball while just before I throw it, but perhaps not after I throw it. So these, I think, most people have got D here. So that after I throw the ball, I'm not pushing it on anymore. So there's no upward force on the ball. There's only the downward force from gravity. Here's another one. This asking that this is a bit more complicated. Turn the camera back on. So this is a bit more complicated. This is the It's a ball that's being held. That way around, okay. Got the ball, and obviously if I'm holding on to it, there's no net force. After I let it go, what are the forces? What are the forces which are acting on the ball after it's released? And this is a little bit more tricky than the last question. So B and C, okay. B and C are popular, okay. So so this is after it's released, so we're not holding on to the ball anymore, so there must be the tension in the string. So that's a force that's in that direction, which both of those diagrams have. And then there's the gravitational force. So the gravitational force, what direction is that? It's always down. So the gravitational force is down, so it's that downward arrow. I guess if you guessed C, then this is the sort of problem you can have with this kind of picture. Students will often answer, more often answer D actually, the sort of, because you expect, you obviously know that the net force is in this direction, so you kind of think, well, there must be a force in that direction, but actually the force in that direction is the combination of the tension and the gravity. So the net force is pointing perpendicular to the string, but there's not a force that's doing that. It's the sum of the tension and the gravitational force. Okay, so I'm not sure if the pictures in these slides don't look very inclusive to me. They always seem to have a fairly fancy looking car. We should change that to some 1980s Toyota or something maybe. So if you've got your car's parked on the hill, hopefully you've put the brakes on. So what's the correct free body diagram in that case? So you can see one of the things we've done here is to draw the x and y axes parallel and perpendicular to the slope, because that's going to make it a lot easier to do the calculation. So what are the forces on the car? Well, there's the gravitational force, isn't there? And then there's the normal force from the slope, and there's the frictional force. And if there wasn't a frictional force, the car would slide down the hill and you'd lose your nice car. Right, so A is mostly right, but A has left off the frictional force, which is what is stopping the car from sliding down the hill. So A would be correct if the car was if the car didn't have the brakes on and it was able to roll down the hill. It would be accelerating then, because there'd be a net force in the positive x direction. So another one. Sorry, I should be wearing the mic, shouldn't I? So the car's being towed to the right. Turn that down, it's a bit distracting. Car's being towed to the right at constant speed, so what's the correct free body diagram in this case? So the clue here is constant speed. So what does constant speed mean? It means if there's a constant speed, the sum of all the forces is 0, the net force is 0. So it must be one of the diagrams, it must be a diagram where all the forces add up to 0. So we've got here the first one has the force from the road, the normal force, and the gravitational force, the weight force. Those are balancing, but there's nothing about the there's nothing about any of the other forces. So D. So most people have picked D. Yeah. So you've got the force from the rope, and that must be balancing the force, the drag force from the air and from the tyres and so on. So that's a nice example. Okay, forces on an elevator. Okay, so this is then an example of an elevator suspended by a cable, and it's very much the same question that I started off with. I was thinking there in terms of the ball on a string, but you know, an elevator on a cable is the same thing as the ball on the string in terms of the way we think about this. So we've got so this elevator is speeding up. So the net force must be upwards, so the tension force and the weight must be bigger than the weight force. So that's pretty much what I drew here. Okay. So the next few slides are really just saying what I said at the beginning. So I'm not going to repeat that too much, but I'll but an important part of drawing these diagrams and getting set up is this assessment part, that once you've drawn this, sort of think, well, is this the right situation? You know, is this a situation where where this is accelerating upwards, or is it a case where it's going at a constant speed? And this seems reasonable at this case. Right, so we've come across this skier before. So we want to figure out the forces on the skier. So we start off with drawing a picture. My pictures are never as good as the pictures in the book, but we've got that tension in the rope and then all the other things. So we draw this little so let's isolate the skier and then figure out what all the forces are. And because it's a slope, we can have the x direction along the slope and the y direction perpendicular to the slope, and then we can start drawing the forces. So there's the normal force, which is always perpendicular to the slope. There's the tension force in whichever direction the tension is. That was the rope. What have we called this one? The kinetic friction. So that's the friction. The skier is sliding, so technically it's this kinetic friction. And then there's the weight. So that's like that. So that's quite complicated. And there's no net force because the skier isn't moving. So this is kind of an important thing that you need to read the problem and figure out what information it gives you. So the fact that it's a constant speed is why we can write down that the net force is equal to 0. Now there's some notes here on the diagram about angles, because those angles are going to be important. And I really haven't drawn this big enough to make that particularly apparent, but if those dots there's an angle theta there, and theta, you're better off looking at the picture here. That theta is the easiest to think of as theta being the angle of the slope from horizontal, right? So if the slope was horizontal, theta would be 0. Theta is this angle here. But it's also this angle between the weight force and the negative of the normal force, the minus y-axis. So useful to keep that in mind when you're trying to think about how to do the calculations, because this is the thing where you're going to get confused and tripped up exactly which angles to use and whether to use cosine or sine when you're doing the calculation. Okay, so here's another little example. Have a block. We push it at constant speed. So we're exerting a force. Why isn't it accelerating? Obviously because of the friction force. So in that case, better if I do it in this direction, for example, so that I can call that x. And then I've got that force that I've applied, and that must be balancing the kinetic friction force, and so the net force is equal to 0. So compare the size, the pushing force and the friction force are the same magnitude. This is what they're meaning by size. The thing that can be confusing here is that we're pushing, so it's looking like that we're applying the force to the block, but the way we draw it is from the block in the direction of the force. So that can be a little bit confusing, but hopefully you get used to that. So now we know something about how to draw these pictures and how to identify all of those forces, and that will then in the next 2 lectures allow us to start doing some actual calculations and work out how big is the acceleration and so on. But before we do that, we have to talk about Newton's third law. So there were these, I always get confused by numbers. I mean, so we had these Newton's laws. The first one is what you might call the law of inertia, that no force gives no acceleration. I personally actually really dislike just numbering things because I always get confused, is it the first or the second or something. The second was that equation F equals ma, which related the force, the mass, and the acceleration. And this third one is action. This is action and reaction. So for every action, there is an equal and opposite reaction. You might, you obviously heard that a few times. Probably about 20 years ago, I was at one of those theatre sport type things where the actors will ask for something, ask for ideas from the audience, and so I actually managed to say, get them to act out for every action there is an equal and opposite reaction. I can't remember what they did. It was sort of more to do with emotions than with physics, but it was kind of fun. Anyway, when we have motion, we often have objects interacting with each other. Even in the case of these balls falling and under the influence of gravity, there's an interaction between the earth and the ball. More obvious if you're actually pushing on something. There's an interaction between my hand and the pad on the table, or here the hammer and the nail. So the hammer exerts a force on the nail, and the nail exerts an equal and opposite force on the hammer. And this can be really confusing if you don't think about it correctly, because you look at this picture and you say, okay, there's a force in this direction, there's an equal opposite force in that direction, so therefore nothing is going to happen. And that's not right, is it? It's not that nothing is going to happen. If I hammer on the nail goes into the wood. Something actually does happen. So the key thing to think about here is that is which object are you talking about when you're talking about these forces? So in this case, you've got the draw my rather useless hammer. Okay, so I've got my hammer, and I've got my nail, and we've been drawing these diagrams saying what are we interested in? So if we're interested in the, that was supposed to be a nail, as in something with a point. If we're interested in the nail, the force on the nail is that force in that direction. If we're interested in what the forces are on the hammer, the force on the hammer is in that direction. Those forces are acting on two different objects. You can't just add them up and say they cancel out. So that's saying the same sort of thing again, except in the case of. I thought I had a different coloured ball, but we'll have to make do with one coloured ball. So there's this force between the balls. One ball is pushing on the other one's pushing on the first one. Okay, so I think I've said most of that. So here's just some more examples. If we're walking, we're pushing on, our feet are pushing on the ground. The ground is pushing in the opposite direction. And similarly with rocket propulsion, the gases that are being pushed out of the rocket providing a force on the rocket ship, and vice versa, the rocket ship is providing the forces on the gas. Obviously, it's quite a complicated thing happening inside the rocket, but we can think of it simply in terms of the force of the gases on the rocket and the force of the rocket on the gases. Sarah stands on a skateboard and Jack starts pushing her. And she speeds up. So the force that Jack exerts on Sarah, is that greater than the force of Sarah on Jack, equal or less? Okay. Okay, there's a few different answers here coming and going. Okay. I think you need to think, if you've picked A, you need to think about what's being asked here. And Jack is pushing on her and she's speeding up. So the net force on her there's a net force on her obviously because she's speeding up. But what we've been trying to get across with this action and reaction is that if you're pushing, there's an equal reaction pushing backwards. So the force of Sarah on Jack and the force of Jack on Sarah are actually the same. So you've got skateboard, Sarah. It's a bit small, isn't it? Jack's pushing on Sarah. There's an equal. So the force on Sarah is that force that from Jack pushing. There's an equal and opposite force on Jack. But if you just consider Sarah, there's a net force on Sarah which is making her accelerate. Here's another one. So the mosquito runs head on into a truck. It doesn't look like a truck, it looks like a taxi, but never mind. So the mosquito or whatever gets splattered onto the windscreen. I don't know if you've noticed, it's noticeable there's actually a lot less insects out in if you go driving around out in the countryside, you used to get your windscreen really dirty with insects, and there's actually a lot less of them, which is a little bit worrying. Where have they gone? I mean, they seem to have died off somewhere, so you might want to think about that as well. But hitting them with your windscreen probably isn't the cause of them not being there anymore. So what do people see? Mosquito exerts the same force on the truck as the truck exerts on the mosquito. Yeah, that's right. So now we're getting somewhere. Okay, so this seems to be a rather short lecture today, which is probably good since it's 9 o'clock in the morning and we don't want to get too tired. So what have we done? We've looked at free body diagrams and we've represented objects. Now maybe, since we've got a couple of minutes, maybe I can go back and, I think this is in some of the other lectures, but we're going to be doing problems with objects on slopes like this, and you might want to start thinking about what are the sort of errors that are easy to make. I think we've kind of come across some of those with the problems we did today, but whenever you do those things on slopes, oops, oh sorry. Yeah, you should. Yeah, when you do those things on slopes, you should always see what's happening. Okay. Right. So we talked about these. Talked about slopes with all these different forces acting on things. So there's several mistakes that happen again and again. I think some of them may have happened to you today when you were thinking about some of those things. So one of the mistakes is that we have the weight force which is going downwards, and sometimes it's easy to get confused and say the weight is perpendicular to the surface. So that's an easy mistake to make. I mean, it doesn't mean you're stupid, it's just easy to get confused. And then the other one is that the normal force has to be perpendicular. So that was our y-axis and our x-axis. The normal force is perpendicular to the slope, but there's an intuitive feeling that the normal force should be vertical. So that's again not quite right. So those are two of the things that it's really easy to get wrong. So really watch out for that. Be really careful about which direction does the normal force act in, which direction does the weight force act on. And it's probably a little bit more, if the velocity was in this direction, then there'll generally be a friction force opposing that. The friction force is always going to be parallel to the slope. So it'd be less common for someone to say, oh, the friction force is going in this direction, because it's a little bit more obvious that the friction force has got something to do with the direction has got something to do with the slope. Okay, so I think we can stop there. So we've talked about these different forces and how to draw free body diagrams, and so tomorrow we'll start doing some actual calculations with numbers. So had a bit of a rest from numbers today, which I think is quite good. I don't want you to think that physics is too much work. So I'll see you again tomorrow at 4, I think. Hello, how's it going? Student ID. Yeah. We don't really need. What do you need the ID for? No. We don't really take attendance in the class, so it's okay. Okay. Hi.
I haven't seen it before. I'm just not sure what it is.
Oh, drop-in. Yeah, that's. Sorry, that's. Where is that? 5 to 6. Yeah, the drop-in classes are optional. So we have a drop-in class on Monday and Tuesday. So if you need some extra help, you can come to the drop-in class. But otherwise, if you don't need extra help, then if you don't need extra help, it's a good idea if you don't come, because it's only it's not that big a room, but it's good. Okay, so that's the idea of that. Yeah.
Thank you very much.
Hi.
So, do you know if there's an IT service?
How do you mean? Oh, you mean you need some help with your stuff? Well, there's they've got a fancy new name which I've forgotten, but in the library building there's a sort of a drop-in thing for just about everything. So if you have problems with your library card or your IT stuff, you know where that is? Yeah, that's the. Yeah.